Let's start right now. I think our director, Dr. Aoun Al-Khassaouni, he's with us right now. He is the Director General of the Regional Center for Space Science and Technology Education for Western Asia. And he's the Arab Union Secretary. Yeah. Right now, we have our guest for today, Dr. Vincent Maurice Blacko. Dr. Vincent, he's a research professor at Department of Physics, University of Notre Dame. He's in Indiana, United States. He graduated from University of Sao Paulo, Brazil. His field, or his specialized field in the so-called chemical evolution of the universe. Dr. Blacko published a lot of papers, around 77 publications, and he has very good score in ADS, around 3,441 citations. His H index, according to EDS, around 27, EITH index 57, and also in Google score, his citation around 3,927. And his H index around 28, EITH index 56, yeah. So as we know, we have a lot of windows to the sky to understand the universe. We have several windows. We started years and years ago by the naked eye. So the first window to sky was the naked eye. Then with the development of technology, we have optical telescopes. This is the second window to sky, and electromagnetic telescopes, whatever it's ground telescopes or space telescopes. Right now it's electromagnetic telescopes. Recently, 4 years ago, we got very beautiful window, which is gravitational wave windows. So we have several windows to understand the cosmology. So tonight our guest will give us an idea about our eyes in the sky, how telescope help us place ourselves in the universe. So right now we have a distinguished speaker tonight, Dr. Vincent Blacko. You are most welcome to the Regional Center platform, Amman. Welcome, Doctor.
Thank you very much for the very kind introduction. I'm really happy to be here. Let me see if I can first share my screen with you. And then please tell me if you can see my title slide in a moment. Okay, share. Okay, so you should be able.
Yeah, that's correct.
Okay, very good, very good. Well, so first of all, I would really like to thank the invitation. I've been working with Mohammed Mardini for a couple of years now, 2-3 years. We've been collaborating in research in chemical evolution of the universe. And it's been a pleasure collaborating with him. And he mentioned that he was part of this great institution, and if I was willing to just give a presentation to all of you. I know that he has given a presentation about his research and some of the research that we do together. So I thought it would be interesting for me today to talk to you a little bit more about just telescopes themselves. And then, as you mentioned, how those new eyes in the skies, so how they help us see better, see further, and see fainter all the way towards the edge of the universe. So I think this presentation is supposed to be a lot of information I've collected over the years about telescopes in general. So we'll talk mostly about optical and near infrared telescopes, even though there are many more types of telescopes, and I'll briefly mention some of those. But I wanted you actually to get you all excited about optical astronomy and just see if we can collectively understand how our understanding of the universe completely shifted once we pointed a telescope towards the sky. So I think that's the main goal I have for our presentation today. And again, thank you very much for extending this very kind invitation. So I'm really happy to be able to share these slides with you. So first things first, I think we already understood that astronomy is an observational science, right? So then when we look at the night sky and we see something like this, in this case it's the Milky Way, we can see with our naked eyes thousands and thousands of stars in the sky. we can see planets, we can see the Milky Way itself. And just by the virtue of our own small eyes, we were able to develop a lot of knowledge. Starting 7,000 years ago in ancient Egypt, for example, we have been collecting measurements of the positions of stars, positions of planets. We've been tracking seasons throughout the year. We were even able to measure the radius of the Earth just by looking at shadows, right? Doing the experiment from Alexandria all the way to Syene. So we were able to accomplish a lot without telescopes. And this is just a virtue of, well, humans being really curious about what's surrounding them. But then all of that knowledge was completely limited by just our ability to see, right? So then when we look at the Milky Way like this, we may think that this is a lot of information, but once we point telescopes to the sky, then the amount of information gets much, much, much larger. And this is what happened back in the 1600s when Galileo first pointed his telescope to the sky. And we, well, try to believe that this was the first observations with a telescope. And by doing that, Galileo was able to just observe so many different things in the sky. And just to mention a few of them, and this is just a scheme of his telescope here on the left side. So he was able, for example, to be the first person who measured sunspots. So those spots in the surface of the sun, phases of Venus, and then identifying some of the moons of Jupiter, just by the virtue of replacing his own eyes with some sort of an optical device that would allow him to see further and to see fainter in the sky. So I think that's where our story starts. And one of the reasons, well, I really enjoy talking about telescopes is because when we talk about telescopes, I think we're able to see how limited our own view is when we're just looking with your eyes. And here I have a comparison. So when we talk about observational astronomy, let's just compare two very optical devices, right? Let's compare the human eye with one big telescope, optical telescope, okay? So if we look at our own eyes, one of the features of our eye is that because it's really small, so the aperture of our own eyes is on average about 10 millimeters. And if you look, for example, at a telescope here, such as the Subaru telescope, the aperture is 8,000, 1,200 millimeters. So it's much, much larger. And just by being larger, is able to collect more light and it's able to see fainter things in the sky, right? Second thing is our eyes, they have a very limited exposure time limit. So we're only able to process information on scales of 0.07 seconds. So every 0.07 seconds, your eyes are just sending information to your brain, and then you're trying to, well, understand that information. And telescopes themselves, they can expose for, well, much, much longer time limits. And then that allows them to record information and make those information available for further analysis. So these are just two differences between our telescopes in our own eyes and optical telescopes throughout the planet, for example. And another main difference that I can point to is that we are limited by our ability to see light coming from the sky in the terms of the electromagnetic spectrum, right? Our own eyes and optical telescopes in general, they're just sensitive to this really narrow optical window, right? So this is the type of light we can see with our eyes and with optical telescopes. So if you want to observe gamma rays, X-rays, infrared radiation, microwave or radio radiation, you would have to use different devices. Or in the case of really high energy astrophysics, you would have to go to space and use space telescopes because that radiation is mostly blocked by the atmosphere. So not only our eyes are small in terms of size, they have limited exposure times in our ability to capture information. And also we can only see a really narrow range of electromagnetic radiation. So all of those things combined, even though we think we see a lot, all of those things, they make us sure that, well, actually, no, we cannot see really further away in the sky or really faint. So that's one of the reasons, well, I'm really excited about optical telescopes, and I think that's why we use them to just progress in our understanding of how the universe evolved. And this, so today's topics, so a couple of things that I want to talk about today are just in general, how telescopes work, how do telescopes work? Most of them, again, optical telescopes, just the one shown here on the right side, I want to just discuss a little bit on what determines the size of a telescope. We know that we have telescopes from all sorts of different sizes. So what determines the size of the telescopes? A few different types of telescopes. And then an interesting part that I usually like to talk about is where would you build a telescope? So what are the main things that we are looking for when we're trying to build new telescopes? And then how those telescopes make part of larger observatories, for example, and how there's some operational aspects within those observatories and telescopes. And at the end, if I still have some time, I want to show you some curiosities that I collected over the years in different observatories throughout the planet. Okay, so let's start with the basics then. So how do telescopes work? So we know that telescopes are just huge, essentially huge light gathering devices. So we point those telescopes all the way to the sky in order to collect light from very faint objects on our celestial sphere. And here is just an example of one big optical telescope. This is the Gemini North telescope in Hawaii. So these are just big, they're just big eyes in the sky, just like the title says. And what's interesting about most optical large telescopes today is that the way that they collect light is very unique. So you're just pointing your telescope to the sky, assuming that all of your sources are at infinity. So then if you assume that all of your light rays are coming in parallel, in the case of optical telescopes, all of that light bounces off this big primary mirror here. It goes to a secondary mirror, and then it goes inside the telescope to a tertiary mirror. And then in here, those red boxes here, those would be your detectors, your instruments, and then you would be able to do different types of science within those instruments. So in principle, you're just pointing to a given object, letting the light come through, and then focusing that light in a way that you can record it in a camera or in a different instrument, so then you can analyze it, right? So if we want to, for example, track the path of that light throughout the sky, throughout the night sky, let's see, here I would point to a given object. Let's see, I pick a star in the sky, and then I just point my big telescope towards that source really precisely. And then I just open that big eye, right? I just open that shutter, and then here you see the big mirror of the telescope. So that light will come all the way from the sky. It will bounce on this primary mirror. You will go to the secondary mirror, and then it will get inside this tube here, and then it will go to one of those nice instruments underneath the telescope. And this is just one example of a big, large optical telescope. And once the light reaches one of those instruments on the bottom of the telescope, what you would do is that light would be redirected to some sort of an instrument, lots and lots of optical devices and optics happening here. For example, if you want to do what we call spectroscopy, you would direct that light to some sort of a diffracting grating, and then you would have some sort of a prism type thing that would diffract the light in all these different colors, and then you would record that light in the form, for example, of a spectrum. This is what you see here on the bottom left. So this is the path. So you point to the sky, that light comes, and then in some really smart way, you use astrophysics, physics, and engineering and optics to record that information, so then you can analyze and reproduce and then spread that information around once you reach our conclusions. So what's very interesting about this, so sometimes we don't think about how those telescopes are built. So what I'm going to show you now is just some of the different ways that those telescopes can be built. So let's imagine that those huge mirrors of those telescopes, they have to come from somewhere. And one of the places is, for example, we have mirror labs spread throughout the world. And this is one example of a mirror lab at the University of Arizona here in the United States. So what you see here, we do have a big cast here. It's a large cast, and we have those small pieces of silica or raw glass, if you want to think about it. And these would be really carefully placed throughout that cast. So then you can produce that mirror, right? So these are all very pristine, small pieces of glass. They're just laid down in there. And then all of that cast is actually, there's a lid closing here, and then they go to an oven. So then this, you have to warm up all of those small pieces of glass so they can melt and they can have the shape of the mirror of a telescope. So then what happens is it goes to a mirror. So it goes to an oven. So this is an oven. So then the oven spins at a constant rate and then at a constant temperature, just so to melt all of those individual pieces and have a very smooth surface of glass. And this process can take up to months. So then you have months of that melted glass spinning around so you can take a very perfect shape of a telescope mirror. And this is what you would see at the end. A very nice mirror of a telescope. So in this case, this telescope here at LSST, I'll just talk about this in a moment. But then you have this very nice and smooth piece of glass. And then you have to provide some sort of a coating, so then it becomes a mirror. But this is one of the ways of producing those very nice telescope mirrors. And in this case here, the diameter of this one is about 8 meters across. So then you can imagine that this is just a huge size. So it's very hard to manage that and to make this a stable mirror so then you can observe really precisely in the sky. So this is how we cast a mirror. So this is how we build a mirror. So now let's think about a little bit about the sizes of those mirrors. If we look at this graph here, this is a very simple graph showing as a function of year, the sizes of the mirrors, the diameter of the mirrors in meters from more or less the 1950s all the way to the 2010s. To me, what's interesting about this particular graph is that at least all the way to the 1970s, most of our telescopes, they had in principle 4 meters, at least the really large research telescopes would have up to 4 meters in diameter. And then all of a sudden, in the middle of the 1990s, we started to go really large in terms of sizes. These are the CAC telescopes. These are just 10-meter diameter mirrors with a different technology that we'll talk about in a moment. And then in the early 2000s, all the way to today, we had telescopes that have mirrors the sizes of 8 to 10 to even larger than 8 meters, all the way to close to 12 for the large binocular telescope. And again, this has to do also with our ability to build those mirrors and have the technology that would allow us to make those mirrors stable and be able to precisely point to the sky. And here is a different picture of telescopes of different sizes, which I really like. And this is just comparing some of those really large mirrors with things that we would know. For example, here's a tennis court at the same scale and a basketball court, just so you have an idea. And these are some of the largest telescopes that we have in the world today. These two here on the right side, this is the 30-meter telescope and the extremely large telescope. These are planned to be built now. They're just being built as we speak. So they're not ready yet. But most, and also here, the giant Magellan telescope as well. But most of the other telescopes we have, Gemini telescope, Subaru, Keck, Southern African Large Telescope in South Africa, and other ones here in the US and also in China, they do have between 4 and 8 and 10 meters across in diameter. And these are really large telescopes. And again, the sizes of those mirrors, they're just really connected to our ability to build those structures, right? If you look in here, there's a really large circle around this entire picture. And this was a planned telescope called the Overwhelmingly Large Telescope. This is from the European Southern Observatory, and this was canceled just because it was just so large that it wouldn't be able to build, it would be cost prohibitive in that sense. So these are just some of the sizes of our telescopes. And again, the size of the telescope also has to do with the way that the telescope gathers light. And there are two main types of telescopes, let's say, that ways that we use to gather light. And these two here are these two types. We have reflecting telescopes and we have refractor telescopes. The reflecting telescopes, they use mirrors. Again, as I said, light comes from the sky, from infinity, parallel rays. They come from the sky. And then since you have a mirror here, you're able to bounce that light around to an eyepiece or to an instrument or to a camera so you can record that information. So the thing is, since you have a reflecting telescope, you can reflect the light. So that makes the design more compact, right? So then you can have a large mirror here in a smaller, more compact design. But if you look at refractor telescopes, these are the ones that usually use lenses. So if you look in here, this would be a lens that is just focusing the light in a way that you could send that to an eyepiece and also to a recording device such as a camera. But then by looking at those two designs, you can see that even though they have the same physical size in length, correct? So the length here is the same, right? Focal length here would be pretty much the same, the physical size. However, the primary mirror on the reflecting telescope can be much larger than the actual lens on the refractor telescope. And that, this is really beneficial to astronomers, because then if you have a larger mirror, you're able to collect more light and see fainter in the sky. Here I just have a couple of animations that can show you how the light, so this will just show you how light is coming towards those two different telescopes, right? It's just coming from infinity. And in the case of the reflecting telescope, it bounces off the mirror. In the case of the refractor telescope, it is just focused close to the eyepiece, so then you can actually see the image or record it. So most of the telescopes that I'm going to show you now, they are just reflecting telescopes because they use mirrors as the light collecting device. And because of that, we're able to build really large and large telescopes. So just so you have an idea of the type of design that those two things would allow us to have, look at those two telescopes. So we have on the left side, we have a reflecting telescope. So that's the Gemini telescope. So the size of the mirror is about 400 inches. That's the reflecting telescope. And if we look on the right side, we have a refracting telescope. And the size of the lens is actually only 40 inches. So it's 10 times smaller. Even though those two telescopes, they occupy the same space within the dome, they have more or less the same physical size, the reflecting telescope allows us to have a collecting area that is, well, 10 times larger. Not only that, if you have lenses, you have all sorts of different optical problems that can happen, because as lenses get too thick, you have optical aberrations and other things that can happen that would compromise the image that you're trying to record, right? And lenses, as they get really thick, they get really heavy. And then it's much harder to just manage those telescopes and make them point very precisely. So one of those reflecting telescopes, for example, is the VLT. So if we think about, that's the very large telescope in Chile. So the size of the mirror, and I apologize that this is in feet and inches, but the 26 feet, so that's about 8 meters in diameter. It's only 7 inches thick, and that's about maybe 20 centimeters thick only. It's really, really small. It's really, really large in terms of size and really, really thin. And it weighs, well, a lot. So this is 51,000 pounds. So then you can imagine that it must be a challenge to make this mirror move around during the night so you can precisely point to objects. And one very interesting engineering feature that we can see on those large mirrors is called active optics. So underneath those mirrors, what you see here are just those mechanical pistons, right? And then what happens is, as the telescope moves, you would imagine that your gravity vector would change, right? Because it's moving in different angles, in different directions. And what those individual actuators do here, they move around with the mirror to compensate for the differences in the gravity vector. So then maintaining the shape of the mirror, so then allowing observations to still be done and the focus of the telescope to still be preserved. So this is a huge engineering feature that happens, and it is in most of those really large optical telescopes. So now that we know more or less about the different types of mirrors, let's just briefly see different types of telescopes. So here are just 4 different types of telescopes you may have seen before. So here on the top left, this is an optical telescope. That's the Hubble Space Telescope, but then it's just flying in space as we speak for over 30 years now, collecting data. This one here on the bottom, that's just a regular optical telescope that most of the ones that we're going to talk about today. Here we have I think it's a near-infrared telescope called SOFIA. And this is a project from NASA. We do have a telescope here just flying in high altitudes in the atmosphere, so you're able to compensate and to avoid most of the atmosphere. And this one here on the bottom, this is a really interesting, so this is a solar telescope. It's decommissioned now, and this is in Arizona here in the United States. And then this is just specialized in observing the sun and doing solar physics and solar astrophysics. And there's a couple other telescope types that I wanted to show you. Most of these, then we go to longer wavelengths, right? When we go to radio, far infrared and microwaves, then you would use lots and lots of antennas in Chile. This is Puerto Rico, the Arecibo Observatory. Here is the Green Bank Observatory here in West Virginia, if I'm not wrong. And this one here is just for completeness, it's another optical telescope. And this is in China. Runs the LAMOST project. So that's also one interesting design of an optical telescope. And what I wanted to show you now is just some examples of those really large, big optical telescopes that are being built right now, and then hopefully be done soon so we can do more science with them. One of them is this telescope called the Vera Rubin Observatory. And this is being built in Chile as we speak. This was formerly known as the LSST. So now it was renamed after Vera Rubin. So this is the Vera Rubin Observatory. It looks like a spaceship, and the mirror is about 8 meters across as well. And this will be a dedicated photometric survey of the entire sky. So we will scan the entire sky in 4 different filters every 3 nights. And this is being built now, and I just have a picture here from a couple of weeks ago, just so you know how it looks like today. So the project is going forward really, really fast, and it's supposed to be a really interesting experiment where all the data will become freely available to everybody once the data is observed. Then we have the giant Magellan telescope that is being built also in Chile. And here, just so you have an idea, this is a big truck here on this artist rendering. So we have 8 mirrors, and each and every one of those mirrors is about 8 meters across. So this is a huge collecting area. So this is supposed to be built close to the current Magellan telescopes. We have another one called the 30-meter telescope. It's supposed to be built in Hawaii. They're having some problems with the actual building, but the project is supposed to be on schedule for the next couple of years, and this is 30 meters across. So that's the next generation of optical devices. And this is supposed to be really, really large. And then it will allow us to see really further away in the night sky. And another one, that's the extremely large telescope in Chile. This is also about 30 meters across. And you can see here, if you look closely on the image, that the mirror is actually a honeycomb type. So we don't have a single piece of mirror of 30 meters across. It's just smaller mirrors that just combined would give that collecting area. And that's much easier to just make that mirror stable. And here is just a couple of trucks, just so you have an idea of the size comparison. Okay? And the last type of telescope I want to show before we move on. Oh yeah, so here I have an idea comparing this huge new telescope, the extremely large telescope, with the Statue of Liberty here, just so you have an idea of the actual size of it. And one other telescope that is planned to be built really soon is the JWST, so the James Webb Space Telescope. So here is a comparison of the Hubble Space Telescope, which is currently flying out in space as we speak. And then the JWST will have a collecting area that is much, much larger than Hubble. And this is just a comparison with the 2 scales, so you can have a look at the size. And this is just a really, really interesting piece of engineering that NASA is just developing as we speak. So the next part of the talk would be, so where would you build a telescope? If you're looking at building optical telescopes, where would you go on the surface of our own planet, because we're bound to our own planet other than the space telescope? So where would you go? And here I have 3 examples of places where you may these days avoid, right? For example, if we look at this picture over here, we see that there's a lot of, well, city here, and that means that we have a lot of light pollution. So light pollution is something that you want to avoid when you're building an optical telescope, because then it allows you to see more clearly in the night sky. You would want a place to be really stable, right? So this telescope here, even though there's snow here and it must be humid to some degree, but then that can be, we can circumvent that. But you would need a place that is really stable. Again, away from city lights like this one. And here on the bottom, this is just an ancient observatory. And what I wanted to point out here is that you see a lot of green in this picture, right? You see plants, you see trees, and that means that there's lots and lots of humidity. And then humidity is something that we all know we need to avoid, because you don't want to build any condensation on your mirror, because that will make your observations be really, well, non-ideal. So if you want to build an optical or an infrared telescope to do world-class research, this is what you need. You need no light pollution, no humidity. You need a really quiet atmosphere, in the sense that there's not a lot of winds or turbulence that can also get in the way of your observations. And you need really high altitude, because then you're just removing atmosphere between you and the objects in the sky, okay? And then, so you have to find places like this on the surface of our planet. And here I have a video, a short video that I want to show you, and this is one of those places. This is an extinct volcano in Hawaii. So notice what happens with the clouds. Even though this is an island in the middle of the ocean, the top of the volcano is so high that most of the clouds, when you look at them in here, what's happening is they're just below the level of the top of the mountain. So if you build a telescope here on the top of this volcano, you're essentially avoiding all of those clouds, because everybody and everything that is underneath those clouds, you wouldn't be able to see the sky really clearly, right? So then that's why you would build a telescope in a place like this. You know, just pause the video and point to the fact that, you see, most of the clouds would be below the level of the mountain, right? And then you see some city lights here. But then if you're building a telescope right really high up here, then you would have a very pristine sky to observe, avoiding most of the clouds and most of the humidity, because you're really high in the sky. So that's one thing. Really high altitudes, really dry atmosphere and calm atmosphere. And something else you have to avoid, you also have to avoid light pollution. To the extent possible, you have to avoid those. And here what I have is a very interesting picture of our own planet, our planet Earth here at night, and just showing you light pollution. So then, as you can see, lots and lots of places have a lot of light pollution, right? You see the obvious places, there's lots and lots of lights. This is, well, where I come from here, the southern part of Brazil, lots and lots of lights, mainland US, Asia, Europe, there's lots and lots of light. So if you want to build a world-class telescope, you should in principle do your best to avoid those lights, all right? And then this is what astronomers try to do when we plan for building new telescopes. And what I want to show you now is, so keep those things in mind, right? You have places here, not only you have to avoid the light pollution, so you have to go to dark places here within this map, but also you need high altitude. Because if you build a telescope, even if it's a really dark spot, but at sea level, then you have lots and lots of atmosphere to overcome. And then you can bring other types of problems to your observations. So this map over here now is showing us the location of some of the large, not all, this is a non-exhaustive list, of some of the largest telescopes that we have on our planet. And I want to draw your attention to a couple of places. So as you can see, there's a really high density of points here. And this is Hawaii, so in the middle of the Pacific Ocean. We have a lot of things in Chile as well, right? Chile, because it's really high, again, really dry. And we have other big telescopes here. So these are just the Canary Islands off the coast of Africa. So then the Canary Islands, lots and lots of telescopes in there. And we also have some in Australia, here one in South Africa, and other ones. I think these are just showing the main, really, I think, larger than 8 meters in diameter. There's a lot of different telescopes that are not being shown here, but I wanted to point out those locations because I want now to really briefly go through pictures of some of those locations and see if we can understand how unique those sites really are. Right? So then you need a really pristine, a really dry site. So one of them, I think this is one of the tallest ones we have, and here I have the altitude in meters. So we do have 5,640 meters of altitude. So this is a really, really high altitude. So the atmosphere in there is really thin. And if us humans, if we go there, we would have a really hard time breathing just because there's not a lot of air. So this is just a perfect place to build a telescope. So then there are some projects that are going to build telescopes in this particular place here in Chile. We do have places also in Asia. So we have this, this observatory here in Tibet, which is higher than 5,000 meters, so 5 kilometers up above sea level, and that allows, you know, observations to be done with a very, very pristine sky. And then once we go out of this place, then we go back to Chile, and this is where the ALMA radio antennas are located. So these are just highlands in Chile, again, above 5,000 meters, so 5 kilometers up in the sky, so you have a really pristine atmosphere. And then if you can find places where they're stable enough that you can put all of those telescopes in there, then it's a win-win for astronomy. And then moving from Chile now to the middle of the Pacific Ocean, we do have this extinct volcano called Mauna Kea in Hawaii. So this is 4,000 meters above sea level. And then if you can see here, this is a tropical place, right? Lots and lots of trees, lots and lots of green. But then as you go up in altitude, all the way to 4,000 meters, this is really dry. This is just like a desert, right? So if you zoom in here, if you see all of those little dots here on the screen, if we go up there, this is what you would see. So we have 13 very large telescopes on the top of that volcano. And then what's interesting, well, there are many interesting features about this, but one of them is, you see the clouds here? So we are above the clouds. So the clouds are sitting at this 9,000 feet level. So this is what they call inversion layer. So then you would see all of your big telescopes, Keck telescope, Subaru, CFHT, Gemini, and others, really above the clouds. So that's perfect to do astronomy because you're avoiding all of that moisture, all of that humidity and condensation on your mirror. And then I have a couple of other ones I wanted to share with you. We have ones here, well, a couple of them here in the US, but some of them in the middle of the desert as well. You see we have Mount Graham here in Arizona. It's not as high, but still really dry. So here we have the large binocular telescope. And then if you go back to Chile, we have Cerro Armazones, where the new extremely large telescope will be built. And then what's really unique about this is that you're just surrounded by nothing. Right? You're surrounded by dry mountains, so no light pollution, no humidity, and that's where most of the telescopes are built, at least the professional grade research telescopes. These are where the VLT, the very large telescopes, are located, again, completely isolated. But then since they are isolated, you have to build a lot of structure around them so you're able to still maintain operations. And some of others that I want to show you here, for example, here's the ocean. So then we're back now to the Canary Islands in Spain. And even though this is not really high, well, compared to the other ones, it's still really dry. Just because, well, you're really high up, so then you don't have a lot of moisture coming from the ocean. Okay, so then this would be, for example, in the Canary Islands. We have a couple of other ones that I wanted to show you, and then I'll move on. So this is Cerro Tololo in Chile as well. So in here, you not only can see, for example, the Blanco telescope, which was one of the first 4-meter class telescopes to be built. You can also see, if you look in this really tiny telescope here, is in fact the Gemini South telescope on a neighboring mountain. So they're all built in sort of a similar places, so then it's easier to do maintenance, and especially because they belong to the same institution. And the last one I want to show you would be, well, I have two more to show you actually. So this one is one telescope in Russia. So this is a project, I think, back in the 1970s, if I'm not wrong. It's a 6.5-meter telescope, but it never gave a lot of interesting results. I think one of the reasons is, as you can see here, lots of green and lots of clouds. So this is not a particularly high environment, and also it's completely surrounded by humidity. So then that makes observations a little bit challenging. And the last one I want to show you, this is the one in South Africa. This is, again, 1,800 meters above sea level However, it's a really, really dry place, as you can see. So then this is a very good spot to do optical astronomy. And this is in South Africa. So this is the Southern African Large Telescope. So it's a 10-meter diameter mirror. So it's a very, very interesting telescope. So then, now that we have all of those telescopes, they cannot work by themselves, right? Astronomers, they drive the assembly of the telescopes because, well, we have research that we want to do. We want to observe stars and galaxies and nebulas, and we want to do observational cosmology, for example. So then we're driving those telescopes to be built. However, there's a lot more people that need to work on those places in order for those telescopes to work every night, right? So that's why, and that's how we establish those things called astronomical observatories. So the telescopes are not there by themselves. So we do have those institutions, astronomical observatories, which are usually partnerships between different countries or different universities. Here you can see a picture on the top. That's the Gemini Observatory in Hawaii, which is a partnership between different countries, right? You also have, for example, the European Southern Observatory, which is a partnership of more than 30 countries, if I'm not wrong, in Europe, in all sorts of different places. So these institutions, they can be large. So they can employ hundreds of people, and most of those people are non-astronomers. We do have scientific staff, astronomers, they're there to help with instruments, to help with observations and make sure the observations are being done correctly. However, you have lots and lots of physicists, you have electronics engineers, mechanical engineers, system engineers, you have people doing HR work, you have people doing all sorts of different things that allow those institutions to work in the first place, right? So they have, well, a lot more than scientific challenges. I think the part that we do, it's at the very end of all of those challenges, right? To make those observatories run, it takes a lot of effort from a lot of people. And these are just some interesting, well, logos I wanted to show you from different telescopes all around the world, right? So these institutions, they are collections of people just working together to do, well, science and to progress science for everybody. And not only here in the US, but in Europe and also in Asia, great institutions just collectively working to, well, improve our knowledge of the universe. So now that we know where those telescopes are and how they're built, let's talk just a little bit about telescope operations. So there's many things you have to consider when you're operating a telescope. Well, one of them would be, how do you control the telescope? Many telescopes today, you still have to go underneath your telescope in order to control it. But many of them, they're just doing remote observing these days. So I can do observations in Hawaii, in Chile, from my own home, just by using my computer and using video, just like we're using now. We can do share screen, just like I'm doing with all of you now, and actually conduct research astronomical observations from our home, which saves money and saves resources. So it's very, very interesting. So again, you have to ask yourselves, who will do the maintenance of all of those telescopes? So you need engineers and you need lots of different people with different expertise. There's lots of safety concerns, safety training, and you have to do drive training as well, because you have to drive to one of those places at some point, right? And then I'll show you some interesting pictures in a moment. So just so you have an idea about how those telescopes would work, at some point during the night, you drive up, and then this is what you would see, right? Those telescopes here, we have the Gemini telescope here, then we have the CFHT, the Canada France Hawaii telescope, we have CAC telescopes, and you have the Subaru. And then you see that as the night progresses, all of those telescopes are just frantically moving around and trying to observe as many objects as they can. Right? Again, this is a particular night with moon, so then that's why it's a little bit bright. But then as you can see, the clouds are moving here underneath, and you can see a very, very pristine sky. If you're curious, you know which star this is, so it's not moving, so the sky is moving around it, so that's the North Star. And at some point, you can see the Big Dipper as well in here, and then you can see the moon. So this is a particular a night where the moon was up. So then what those telescopes would do, once you reach your destination and you're sitting underneath that telescope, would be just spending your entire night observing. And what I wanted to show you now, and I'm just going towards the end of my presentation, was how you reach that destination, right? So some of the things that I collected over the years when I worked for one of those telescopes, I wanted to share with you in a moment. And this is what you would see. And then here you see the sun starting to rise here, and then it would be the end of your observations. So in this particular case here, for the Gemini telescope, what I wanted to show you is how you get there, right? Let's assume that you're working at a telescope and you have a night, an observing night, that you have to do your shift. So first, what you would do, you would sleep most of the day, right? You would spend the day sleeping in one of those houses. So they have lots and lots of different houses, so you can spend the day just sleeping. And then once you're awake, and then towards the end of the afternoon, what you would do, you would just drive up the mountain. So if you look in here, so this picture here, so these places here are the places that I just showed you where you sleep, right? And once you're done sleeping during the day, you would get your car, and then you'd have to drive about 35 minutes all the way to the top of this particular volcano so you can work, right? So then once you're all rested and all fed, then you just get your car and then you start driving up. So let's drive up together. So then you start driving up, and what you notice is there are no plants, no vegetation, pretty much nothing. It's a really dry place, right? The atmosphere is really thin. So then as you drive, what you see is pretty much nothing. In this particular case was during the winter, so there was some snow, but even though we had snow, it's still really dry. It's cold, but it's really, really dry. And then you keep driving up and driving up, and then you start to see, well, those huge telescopes in there. And this is just paved road, so then you have to avoid some sort of a dust being lifted up when the trucks are driving in. And then you reach your destination. Well, almost reaching our destination. So you see again different telescopes, the Keck telescopes and the Subaru telescope. And once you reach your destination, there you go. So this is the one we are going to get in right now. So that's the Gemini North telescope. Then you would park your truck here, you would get in, and that's where you're going to be from, I don't know, 5 p.m. all the way to 7 a.m. the next day, depending if it's summer or winter. So then once you get there, this is what you would see from inside the telescope. Lots and lots of people usually gather to see the sunset from outside, lots of tourists. But then you would be inside the telescope just preparing for your observations. And here just you have an idea, this is, well, me, an average size human. And then you see the size of the telescope, just so you know how large that telescope really is. And then what you have to do, you have to open those shutters here. So then you would see the mirror here, very clean, very pristine mirror. Then you would put those things, point those things toward the sky, and then start looking at your objects. And then you would be doing that from a place like this. So this is what we call the control room. So this is pretty much underneath the telescope. Then you'd have two main observing stations. One station here, this is for the astronomer. So the astronomer is just controlling the type of science that is being conducted on that particular night. And this station over here is the telescope operator. So the telescope operator makes sure that the telescope is running fine and the instruments are working, and then everything is working well. And then you keep monitoring here screens, for example, this on the top, everything is green, so everything is good to go. So you'd be just spending your night doing those observations. And there's other types of observing rooms like this one, for example. You have lots and lots of different monitors here, so you can see what's happening with the weather, with your instruments, with your telescope. So there's ways of monitoring each and every one of those aspects of that big telescope. And what I have here for you is just a couple more different observing rooms that I visited over the years that I wanted to show you. So this is one in Chile, again, the same type of a structure. So you have lots and lots of monitoring things. And the work of the astronomers is just to keep looking at those computer screens for 12 hours. Right? It's not as romantic as we would like to be, to go outside and appreciate the sky. But then if you're doing work, if you're doing your research, you have to be sitting there, just making sure that everything is working fine. Okay. And I'm almost reaching the end of my presentation. I'll just have a couple more minutes. I wanted to show you just one more observing room, and this is an older one. This is from, and again, it's still working today, and that's the Keep Peak National Observatory in Arizona. As you can see, these are older types of instruments, but still doing lots and lots of interesting research. And in this particular case, the observing room, if you look at this window here, what you would see the telescope. That's the Magellan telescope, which is 4 meters in diameter, and that's a telescope in Arizona. I just have a question. So how much time do I have still? Just so I didn't see what time we started. Dr. Ibrahim?
We are so happy to have such a distinguished guest in our platform. We have Professor Osama Shalabi from Egypt wants to ask a question. Please, Dr. Osama.
Mm-hmm.
Yes, Dr. Osama, welcome, please.
Oh, can you hear me?
Yes, yes, Osama.
Oh, first of all, I would like to thank you very much for this tour for the whole world to see these kinds of diversity of telescopes from small to large and from side to another. That's very really interesting to have this global overview of such different types and different kinds of telescopes. My question or my point here is that it is not only the telescope facilities, but it is also the infrastructure for that telescopes that we can gain from that equipment of the high tech or that leads us to a better analysis of the data we are collecting. So I would like to ask for how this managing the work with Institute of Research, the proposals, how they select one and reviews the others, etc. How this selections, rules, and so on, where we can find our place in this, in the Arab community, in these large networks and highly advanced technology of optical telescope, at least. Thank you.
Yeah, that's a very good question. I can give you some examples, at least for some observatories I know. I know that, for example, here in the United States, we have our national observatory, and that observatory takes care of all the open access time for the US facilities. And that time, they actually have what we call an open skies policy. So anybody in the entire planet can actually apply for time in one of those telescopes. So what you would do is we have twice a year, you can submit an observing proposal. So then you would just write a form saying, hey, this is the type of science I want to do. This is the type of telescope I want to use. And this is the type of instrument setup I want to use. And then you propose your observations and say, hey, I'm submitting this project to this time allocation committee for your evaluation. So then what the committee does, they convene, they read all the proposals, and they rank the proposals in order of scientific merit. And then once those proposals are ranked, they are assigned time based on their grades. And once you have your grade, then you would be notified by the observatory if you have, for example, if you were granted time or not. So then this is a competitive process that runs twice a year. I know, for example, for the European Southern Observatory, the process is the same. So the member countries, they just compete for time. So they submit proposals, and again, there's a time allocation committee that reads the proposals and then ranks them. And then this is how they assign time. And once that time is assigned, what you would do is then you would be contacted by the observatory, and then you would be able to prepare your observations. Some of those observations would be you as a principal investigator going to the observatory and doing observations, and other observations would be just conducted by the observatory staff. You would just tell them, I want to observe this object for this many hours, and then they would do that whenever it's more convenient in terms of scheduling. So I hope that answered the question.
How about the financial support?
Oh, Yeah, so the financial support, that's another interesting question. So in our case here for the United States, the National Observatory is supported by the National Science Foundation. So this is money coming from the federal government. However, there are other observatories, for example, here in the US, and telescopes that are supported by universities. So then there's a network of universities, and each university pays a given fee, and then they are allowed to have some sort of a fraction of the time for the observatory. Because those operations, they can be very expensive. I think in one observatory, so just for one night of observations, if you count all of the costs, those could be anywhere between $50,000 and $100,000 per night of observation.
Right.
So it's a very expensive endeavor. And I know, for example, that for the European Southern Observatory, each country contributes with their own share, and most of those funds come from funding agencies within those countries. It could be the Ministry of Science and Technology, it could be the Ministry of Education, and that depends on each country.
Thank you. Abbas Faouri from Syria, please welcome.
Hello, Dr. Morris. Hello, everyone.
Hello.
Thank you for this lecture. Actually, I have two questions. The first one, how did we take a photo to the black hole? And the real question, how can we make a large telescope from many small telescopes? This is the first question. The second one, how can we protect the sky from SpaceX satellites?
Okay, so let's see. How can we take a picture of a black hole? Well, since the black hole is dark, we cannot take a picture directly of the black hole. We can look, for example, now for the gravitational waves, and we know that that's one way. But another way is you can take pictures of the stars around the black hole, and then you can see how they're moving. So if you know the laws of physics, Einstein's, general relativity, then you would know how those stars would be behaving if a black hole were to be in the center of those orbits. So then you can observe what's happening around the black hole. You can observe X-ray emissions, gamma ray emissions, and something like that, right? So that was the first question, right? The second question is, how can we build a telescope using a big telescope based on smaller telescopes, right?
Yes.
So we can use techniques such as interferometry, where you just have telescopes, for example, even in different countries or in different places throughout our planet, and you can combine the light from those telescopes in order to mimic a really large mirror. That's, for example, what LIGO does, and Virgo, what they do in gravitational wave space. So they have detectors in different places on the planet, so they can combine that light using interferometry. We can do optical interferometry, radio interferometry, and other things. But maybe another answer to your question would be, we can build a really big mirror by having really small pieces of glass, just like the new 30-meter telescope, for example. You have hundreds of really small pieces of glass. They're just combined together to make a really large mirror. If they have the proper shape, they should be able to have the same collecting area and the same capability, right?
Yeah.
So then the other question was the Starlink, right? The satellites. And I think this has been a huge discussion these days and a huge point of contention, because, well, I don't know what the answer of that will be. What I think it should happen is everybody should be able to speak, right? And to give their own opinions. Because the satellites, well, I think the goal of the satellites is to provide global internet access to everybody, right? And this, to me, seems like a good idea, of course. However, you should be able to accommodate other things happening. For example, research in astronomy. We know that there's a lot of investment and a lot of research being done, basic research that goes back to universities and research centers with astronomy. So maybe not all of those satellites should, for example, block our view. So there's still being a huge discussion about how this will be handled, because there are many satellites in the sky already, and we can see the effects of them in many images from the sky. And I know that there are discussions happening now to maybe change the satellites. I know that some of them, they're just trying to paint the satellites with a very dark coat of paint, really opaque, but I think that didn't work very well, as far as I understand. But I think, at least to me, my naive opinion would be, we should be able to talk amongst themselves and just reach a solution that would benefit everybody, right? Because both things, they should be able to coexist, right?
I think IAU asked Elon Musk to reduce the pollution of such satellite, and he proposed that the next batch will be at least one satellite will be coated, and also in addition to coating, also the orientation of the sun. So yeah, it's coating and orientation. He promises that next batch will be hidden. We can see, because to keep our sky free of pollution. Okay, we have right now Hassanin. Please, Hassanin, are you okay? Please introduce yourself and ask your question.
Hi, Doctor, and hi, everyone. I am a lecturer in the University of Baghdad College of Science, Department of Astronomy and Space. I've got master thesis. I've got master from University of Chile in Poland. If you don't mind, I have two questions. The first question, as I know, the James Webb Space Telescope, and I have this information about it, will find the first galaxies that formed in the early universe and peer through dusty clouds to see stars forming planetary systems. My question is, why especially James Webb Space Telescope will find the first galaxies? I mean, the another telescopes like Hubble telescope or another telescopes didn't find the information about the early universe. The second question, if you don't mind, the gravitational wave detectors, it is detectors or telescope or both? Thank you very much.
Sure. I think, so your first question, well, again, as far as I know, what's really unique about the James Webb Space Telescope is, well, two things. Is a space telescope, right? So then you don't have the atmosphere, so then you have well, a better view of the universe, and it's really large. So it's much larger than Hubble, for example, right? And the reason that it can see all the way towards the edge of the universe is because not only it's really large, but then it's able to look at the same spot for a really long period of time, right? If you remember the Hubble ultra deep field, so then Hubble was just staring at the same place for days and weeks, so then we can collect light that is really, really faint. And I think what James Webb will be able to do is, it will be able to do that with a larger mirror. So that will allow us to see things that are even further away or even fainter in the sky. Because in the end, so the James Webb Space Telescope is just an upscaled version of Hubble. So then by avoiding the atmosphere and having this really large collecting area, it should be able to do that, right? I think nowadays we're still not able to do it because we have limitations in terms of the amount of time we can observe here from our planet. And then the fact that we have to observe only at night, not during the day, right? And then space telescopes wouldn't have many of those limitations. So then I think that's one of the reasons JWST will be able to see even further.
One more, Maurice. I think for James Webb Telescope, it's 6 point something the mirror diameter. And one of the most important thing of James Webb Telescope, it's shifted to infrared region.
Sure.
It's in infrared region more than Hubble telescope. Telescope very limited in the infrared region, but James Webb is so completely larger, shifted to infrared region, so we can see very, very distant galaxies, and we can go further to deep in the history of the universe.
Absolutely, yeah. And again, one of the reasons that people like myself, for example, use Hubble Space Telescope is because it's optimized for ultraviolet. So you have ultraviolet spectroscopy, and then for chemistry of things in the Milky Way is really nice. But then for James Webb, yes, and you're correct, it's just optimized for infrared astronomy mostly. And I think, so the second question was about gravitational
waves. Yeah.
Can you repeat the question, just at the end of it?
Hassanin, please repeat the question. Hassanin?
Yes.
Yes, repeat the second question, please.
Thank you very much. The second question is, gravitational wave detectors, we can say it is considered telescopes or drives, or what, or the both, or the detectors, I mean, or the telescopes, or the both? Thank you.
Well, I think in a way you can consider those telescopes, they're just optimized to see different types of messengers coming from the sky, right? So we're not talking, when you talk about gravitational waves, you're not talking about electromagnetic radiation anymore. So then when we think about telescopes, we usually think about electromagnetic radiation, right? Gamma rays, X-rays, optical, and infrared. So in that sense, maybe you cannot say it's a telescope. But I think in the end, the detectors in the actual LIGO and Virgo, these are just collecting messages from the sky. That's the way I like to see it. It's just in different ways, using different physics, right?
We have a question in the...
More questions, please?
There's a question in the chat window, please.
Yeah, if there's some question in the chat room. Yeah, I think 2 questions from Rami Saadi. He's from Jordanian Astronomical Society.
Okay. Okay, I can read them in here.
Yes,
so
please.
First question is, you talked about active optics. Is it the same as adaptive optics? Okay, so this, no. So active optics is that optics that is just acting actively in the mirror, so then to maintain its shape. That's active optics. And adaptive optics is a different type of corrections that are done in the mirror to account for the atmospheric turbulence. So then you're just deforming your mirror in ways that would help you cancel the effects of the atmosphere. So these are just 2 different things. Yeah, but that's a very good question. So second question, is there any tools to compensate for the lack of oxygen in high altitude observatories? Well, so one of the things many of the observatories have been doing now is just do observations from home, like here, right? For example, some of the observatories in Hawaii, they do most of their observing during the night from their offices in the city, which is at sea level. So then you're avoiding that travel up and down. But then once you're up there, you usually have to, well, adapt to that. So they have oxygen masks if you need to, and then it's hard to breathe. But then you usually have to, well, adapt. Yeah, but these days, many observations are being conducted from places that are not actually at those high altitudes. Yeah, okay, good.
More question, please. Okay, if we don't have questions, we'd like to thank Dr. Bleko so much for this nice lecture, and we are very close. You know, COVID-19 made the globe is a small village, so we can communicate. We have a lot of interactions, online events and activities. So, like by the name of Regional Center of Space Science in Jordan, thank you so much for the great lecture, and we'll keep in touch for future and coming lecture. Thank you so much, Dr. Bleko from University of Notre Dame, Department of Physics, and he's expert. Maybe next time we need a lecture on chemical evolution of universe. I'm interested in large-scale universe. I like the word of Peplis. He said that one day, I hate Big Bang. I'm looking for something called cosmic evolution rather than Big Bang, because Big Bang, we are talking about small fraction of events, but right now it's a huge, large scale called cosmic evolution. So chemical evolution is a part of the big scale, bigger than it's called cosmic evolution. It started from the T = 0 up to the human intelligence and the human culture. This is the story of cosmic evolution. So thank you so much, Dr. Bleko, for the nice lecture, and waiting for another nice lecture like this one. Thank you so much.
Yeah,
Dr. Ibrahim, if you'd like to talk something, Dr. Bleko?
Oh yeah, no, I just wanted to thank you all again for taking the time. I know it's a Sunday night for most of you, so thank you very much for taking the time. I think this is a very interesting subject, so I leave my email with you. So if you have other questions, just feel free to contact me. And I would be really happy to give another research-focused presentation to you. So just let me know. And again, thank you very much.
Yeah, we have workshops specialized. This today is just a public lecture, but I think coming we have several workshops. Maybe we have looking for some scientific collaboration in a specialized field, it would be much better. But for this, it's about for public. Yeah.
Sure, absolutely. Yeah, I'm in contact with Mohammed Mardini, so we work together a lot. So
Yeah.
we can for sure set up something. Yes, absolutely.
Thank you so much. Thank you. Dr. Ibrahim, the mic with you, please.
I would like to thank Dr. Blacko and all participants. We have a lot of participants, Arab science from all Arab world. I will like to thank them all for joining us for this lecture. And I wish we will have you again and again. It's a very interesting lecture. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.